Welcome to your EASA M7.8 Riveting B1 Test Prep Explainer. We're skipping the fluff and diving straight into the mechanics of riveting. Look, if you're gearing up for your exams, you already know this module is super heavy on precise specifications and structural physics. Our goal today is to make sure you understand exactly why these technical choices are the correct ones, so you can absolutely nail this test. Let's get into it. To achieve high structural efficiency in aircraft manufacturing or repair, there are absolutely no shortcuts. Before any part goes into service, every single rivet requires inspection. Why? Because structural efficiency leaves absolutely zero room for error. You aren't just looking at a fastener, right? You're looking at the literal integrity of the aircraft's pressure vessel and its load-bearing skin. So 100% inspection is the only acceptable standard.
All right, Section 1, Rivet Selection and Specs.
When the exam asks what standard aircraft rivets are made of, the answer is aluminum alloy. But the reasoning behind this is what's really important. We obviously can't use heavy steel everywhere, and purely soft copper just won't hold up for structural riveting. We need that perfect balance. Aluminum alloy gives us exactly that, the ideal combination of incredibly low weight and high structural resilience that aerospace applications demand.
Okay, I want you to visually cement this number in your mind right now. 100 degrees. This is the international standard angle for countersunk rivet heads. And, logically, it's also the exact included angle of the countersink tools we use to carve out the recess for them. Remembering this 100-degree standard is pretty much guaranteed points on your exam. Now, a massive part of this is understanding exactly when to use specific head shapes. Countersunk heads, those are all about maintaining a smooth aerodynamic profile. But mushroom head rivets, those are specifically selected for outer skin coverings where flushness isn't the main aerodynamic factor, but shear strength absolutely is. They give you the absolute maximum strength possible for those skin panels.
Moving right along to Section 2, Sizing and Spacing Rules.
Watch out, because this is a classic exam trap. Drilling a hole for a rivet is fundamentally different from drilling a hole for a screw thread or a standard bolt. Unlike bolts, a rivet hole requires a very specific rivet clearance. This is the deliberate size difference between the hole and the rivet diameter. Why do we need it? Because when you drive that rivet, the shank actually has to swell up and perfectly fill that void to lock the plates together. No clearance? The rivet won't even go in. Too much clearance? It won't swell enough to grab the metal.
You'll definitely want to lock these multipliers into your memory. Think of this as your cheat sheet for spacing and sizing questions. First up, to figure out your total rivet length, you just add the rivet allowance to the combined thickness of your sheets. Easy enough. For a snap head, that allowance is 1.5 times the rivet shank diameter. Now for layout. The absolute smallest allowable rivet pitch is 3 times the rivet diameter. But, and pay attention here, if the question specifically asks for the minimum spacing between protruding head rivets, that multiplier bumps up to 3.5 times the rivet diameter.
And here is a brilliant example of how manufacturing processes directly dictate design rules. You have to keep in mind that the required pitch for countersunk rivets is fundamentally larger than for universal head rivets. The reasoning comes down to pure structural physics. The countersinking process literally removes parent material to create that 100-degree dish, right? So to keep the sheet metal between those holes structurally sound, you mechanically require more distance, a larger pitch between those countersunk rivets.
Okay, Section 3. Tools and procedures. When we discuss the standard solid riveting procedure, also known as reaction riveting, you've got to understand the flow of energy. The preformed head or manufactured head takes the direct primary blows from the rivet gun through a tool called a snap. That kinetic energy physically travels right down the shank to the other side, where your heavy bucking bar is waiting. That bucking bar provides the crucial opposing mass, forcing the shank to swell and ultimately forming your shop head.
But here's a scenario. What if you need a flush 100-degree countersunk rivet, but your aluminum sheet metal is paper thin? If you try to machine countersink it, you'll widen the hole so much you create a dangerous knife edge, completely destroying the material's strength. The fix for this is dimpling. Dimpling uses a matched male and female die, basically a punch set, to physically press the metal inward, creating that needed recess without actually carving away any material.
Faulty riveting is a total nightmare. It's expensive and incredibly time-consuming to fix. So how do we stop it before it starts? Well, the #1 cause of faulty riveting is using the wrong size dolly or snap. Your tooling must perfectly match the rivet head. This is exactly why your absolute best preventative measure is to always perform a dummy run before final installation. It verifies your tooling and alignment are spot on.
And finally, Section 4, identifying and fixing faults.
On your exam, you'll see physical faults paired up with their specific root causes. Let's map these out quickly. Excessive or insufficient shank allowance, that guarantees you'll get an improperly formed shop head. If you see devastating cracks radiating through a rivet head, that's the direct result of excessive driving pressure, hitting it way too hard. And what if the metal sheets are separating? That happens when the work wasn't clamped firmly together. The rivet shank swells in that tiny gap between the sheets, literally jacking them apart permanently.
Let's talk about the physics of the bucking bar one more time. What actually happens if the bucking bar you grab is just too light? Well, it won't have the necessary mass to absorb the impact from the gun. So instead of that kinetic energy swelling the rivet shank, that violent force just pushes the bar away and deforms the surrounding thin sheet metal, making it bulge outward, directly toward the shop head.
As a mechanic, visual inspection is everything. If you're scanning an airframe and you spot a distinct, dark, soot-like ring deposited right around the perimeter of a rivet, you've found what we call a smoking rivet. This is a working, loose rivet. It has structurally failed. As the aircraft flexes, that loose rivet is violently grinding against the aluminum skin, creating that dark, powdery metallic dust.
So let's say you drill out one of those failed rivets, and you notice the hole has elongated due to stress. If you try to just pop a new rivet of the exact same size back into that stretched hole, its ability to carry its share of the shear load is severely compromised. The structural math just doesn't work anymore. Because of this, you are mechanically required to step up and replace it with the next larger size rivet to restore the airframe's full structural integrity.
Which brings us to a hard and fast rule in aviation maintenance. If you find rivets with damaged heads, there are absolutely no acceptable rework or adjustment procedures. None. A mangled preformed head is structurally compromised. It must be completely drilled out and replaced. No exceptions.
And that wraps up our targeted test prep explainer. As you head into your B1 exams, I want you to keep asking yourself, are you just looking at a tiny piece of metal, or are you ensuring the absolute continuous integrity of an aircraft skin? Mastering these clearances, pitch rules, and fault identification techniques isn't just about picking the right multiple-choice answer. It's about understanding the real-world physics of holding a pressurized aircraft together safely at 30,000 feet. Good luck out there, and keep striving for that 100% structural efficiency.